Okay, so we are going to look into technical details about the feedforward neural network. That is, we are going to use some mathematical equation to describe the input and output, yeah, according to the network topology. Now, this is a general form of the a three layers fully connected feedforward neural network. And so when we talk about the multi-layer perceptron neural network, at least we have one layer of input and then the output layer right here, and then we can have many hidden layers as you want. Again, this is a three-layer topology, so we only have one input layer, one hidden layer, and one output layer. So when you look at each layer, that is, each layer it consists of a number of neurons. Right here, the input layer, the green circles right here, that is the neuron, and then the purple circle right here, that is the neuron in the hidden layer, and then the um, um, the pink one, that is the output layer neuron. And the function f, we call this is the activation function. I'm going to talk about this later on. Corresponding to layer, we have the link, this link, that is, which is associated with a connection weight, W. Yeah, so here we call this is the WJI. Yes, the JI, they are the value. I'm going to talk about this, the index of JI, and right here that is WKJ. So corresponding to each link, we have a weight right here. Yeah. So when we look at this connection, when we look at this neural network topology, when we present x1, x2, xd into this neural network, and then we also corresponding to the hidden layer, we also have the bias, and then this bias in other textbook, they use -1, but it doesn't matter. We are going to use 1 in this lecture, and then so when we have all these input, including the bias, we will present it into the hidden layer. The hidden layer, the function f will process on this input and generate y1, y2, up to ynh. Ynh, that is the, the number of hidden node. And then in the output layer, we have the bias as well. So that means when you consider y1 up to ynh and the bias 1 right here, so we can regard it as the input of the output layer. So all these values will be fed into this output layer and generate Z1, Z2, ZC. So this network, that is, we have the input, yeah, we have the input, and then it produces C output. Okay, so multi-input, multi-output neural network. Again, don't forget about the bias. Yeah, the bias, that is, we are going to implement that no matter what number of input it is, as well as what number of output it is. Yeah. Okay. So we're going to take a closer look into the hidden layer, that is the hidden node. For this one, actually, x1, the green one right here, we do not have any activation function. That means at all this point, this will be x1. All this point right here, that is x2, and so on. So we are going to look into one of this particular purple node. We call this is the hidden node. Yeah. So for example, if we are going to follow this x1 and then this line, x2, this line, xd, and the bias. For example, this hidden node, I'm going to draw it right here, and then instead of calling it y2, I just call this as yj. When j, that is going from 1, 2 up to nh, and then it means that you are going to specify different hidden node right here, but the structure is exactly the same. So we are going to look at this particular hidden node right here with x1, x2 up to xd. Yeah, so we can see the x1, x2, xd as well as the bias right here. So we will have this structure. When we zoom into this particular hidden node, we have two elements. The first one, that is the summation, and then the next one, we call this is the activation function, and then the output y right here, that is the output of this hidden node. So what we are going to do is that we are going to calculate let j. Let j, that is x1 times the connection weight wj1, and then plus x2 times wj2, and then plus up to xd times wjd, and the bias 1 times wjd. So we are talking about these terms. Okay, so let j, that is the sum of x, sum of the multiplication of x and w. So we obtain let j. So we are going to talk a little bit about the subscript right here. So you can just find out that the first subscript j, it means that this is the hidden node j. The next subscript 1 right here, it means that this length, this w, is corresponding to the first input x1. So we follow this pattern. wj2, that is the connection weight between log j and the input 2. This one, log j and the input d. We use 0 to represent that this is the connection weight for the bias and the hidden node j. Yeah, the first subscript, the hidden node number, and then the next subscript, the input. Yeah, okay. So once we obtain let j, and then we are going to further process this value of let j by passing it through this activation function f. We are going to define what this activation function it is. So j can be represented in this compact form. Yj, that is function of let j, that is this input, and let j, that is we lay it into x1 and w, x and w, that is we relate let j due to x as well as the bias. Yeah, so that means once we know what input x it is as well as the value of w, and then we can compute yj if we defined the function f right here. Yeah, so corresponding to the hidden layer, we have all the hidden node will have the same function f, but actually if you wish, we can choose different function for different hidden node. Yeah, okay. Now just to give a little bit more details, why we always mention about the 3 layers neural network. Yeah, for the 3 layers neural network, it consists of the input layer, that is the input samples we present right here, and then so the hidden layer, that is the layer in the middle, and then the output layer, that is the node which is going to generate the output. And don't forget about this bias. And so we call this is a 3-layer neural network, and we have a short form for this typical structure. For example, we call this is D-NHC neural network. For example, this one we have 2 input, so D, that is 2, and then so 4, that is the number of hidden node in the middle, 1, 2, 3, 4. So NH, that is 4. So we call this is 4. And then 1, that is the number of output. We only have 1 output, so this is 2, 4, 1 neural network. And when we consider a 3 layers neural network, we will just find out that theoretically we only need 3 layers, because a 3-layer neural network theoretically is proved to be a universal approximator. It means that a 3-layer neural network can approximate any continuous function in a compact domain to any arbitrary position. So a 3-layer is sufficient, but sometimes why we are going to increase the number of hidden layers to more than 1. For example, in between we can have 10 hidden layers. In that case, we are going to increase the expressing capability in some sense, or for some reason we are going to use more than 1 hidden layer. Yeah, so now the question remaining is that we know that corresponding to this link each link will have the connection weight. How do we determine that? That is, we are going to use the backpropagation algorithm. In some textbook, it refers to backward propagation algorithm. Yeah, so this is an algorithm depends on the gradient descent. Yeah, so I'm going to present this to you in the next section. Yeah, but anyway, this is the topology of a three-layer neural network. We can generalize this idea to a multiple layer neural network. Now, we are going to talk a little bit about the equation. Yeah, as you know that this neural network, let J, that is something about the equation at this point. In some cases, we are going to rewrite this equation into a compact form so that we can represent the equation in a clear way, yeah, in a clean way. For example, just record this. This is the x times w, yeah, x times w, and then so because we have one right here, so one times the bias times the connection weight corresponding to that bias, that is 1, so we do not have x. Yeah, so if we are going to consider I start from 1 to d, I, that is this value, I equals 1, I equals 2, I equals d, so we can just simply write into a compact form using the summation from I to d, and then the last term, that is the bias term. We can also include the bias into this summation, that is to start with I equals 0, and then so because when we talk about I equals 0, we expect that x0, that is 1. Yeah, so we can come up with this equation, come up with this term, or we can also use a very compact form, that is in matrix form or vector form. If we are going to have wj, that is consists of wj1 up to wjd, and then the last term that is wj0. In some other textbook, they put wj0 at the top. Yeah. So anyway, if we are going to construct x in this particular form, we are going to have x1, 2, d, and then the last one, that is for the bias, and then so we come up with this form. And so the let J can be represented by this compact form, and so we also have the Yj, that is the output of the neural network, that is the output at this particular point. Yeah, so when J, that is 1, we are talking about Y1, when J, that is 2, we're talking about Y2, and so on. All of them, we can use this set of equation to represent that. Okay. Now we have talked about y1 to ynx and those equations about the input and output of y1 to all these x, and then we are going to extend this idea into the hidden layer and output layer. For example, once we have y1, y2, ynx, including the bias, if we are going to look at this orange link, this one, this one, this one, this one, and extract this hidden node and put it right here, and then we come up with the output locate structure right here. Yeah, so this y1, y2, ynx, that is right here, and this one, that is this bias, and then this hidden node, this output node, that is we put it right here, expand and zoom into that. We have similar structure, that is a summation side, and then the output, that is let Kate. After we obtain let K, feed it into this activation function f, that is this guy. Yeah, that is this guy. This function in the output layer can be different from the f the hidden function, the function f in the output layer can be different from f in the hidden layer. Yeah, so it depends on our choices. Yeah, so fit nk into this activation function, we can compute zk. So we come up this equation. So we are going to do the same for let Kate. That is let Kate, that is equivalent to y1 times wk1 plus y2 times wk2, and so on. So we come up with this equation in compact form, in summation form, and then it depends on which format you like to use. So anyway, this is the we have these two sets of equation to govern the output Z1 up to ZC. So that means when you have X1 to XD, present that into this neural network, you can compute Y1 up to YNH. Once you know WKJ, and then you can find out what value of ZK it is. Yeah, so we are going to feed in the samples X1 to XD and then compute Z1 to ZC. Yeah, okay, again, the notation right here. WK1, the first subscript K, it depends that this link that is for the output layer. For the output layer, the K look right here. Yeah, the output look K. And then so the second subscript 1, it means that this link is corresponding to the first Y1, the Y1. And then the same applies to K2, K, that is for output locate. 2, it means that it is for the Y2, and so on. Yeah. So this is the, once you know this set of equation, you can compute the value of Z1 to ZC. Now we are going to talk a little bit more about what F we can use in the output and hidden layer. Yeah. So in general, these are some commonly used activation function. Why I put transfer function right here? Because in MATLAB they call this is the transfer function as well. Yeah. So the activation function, we have the hard limit or the side lump transfer function. We can put it right here. So this is the shape of the transfer function of the hard limit. Yeah. So and that is the input right here, and that is the let. Yeah, so that is the let value. So the let value that is inside this hidden node. So that means once you have this let value, no matter it is in the hidden layer or in the output layer, we can compute this value, and then we fit this value into one of this function. For example, this the signal function. If it is more than 0, and then it will give you 1. It means that ZK or the YJ, it will give you this value. If it is less than 0, and then it will give you -1, or we are going to use the linear function. Yeah, so if it is a linear function, that means what value as the input, it will give you just what value as the output. Yeah. Anyway, F, you can choose one of these functions so that it produce it is going to give you some nonlinearity to the neural network you are going to design. Yeah. Which one is the best activation function? I do not have any recommendation, and then it really depends on the application at hand. Yeah, but later on you will just find out that if we are going to use the backpropagation algorithm to train the parameters W, Ji, and Wkj, and then so we require that the activation function to be differentiable. Yeah, because we are going to use the gradient based technique to update this W. If it is not differentiable, and then the algorithm does not work. And now I'm going to put all the things together. That is what I have mentioned before. When we present X into this neural network, how do we calculate Z1 or the overall equation? Yeah. So just to recall that, this is the hidden node. The hidden node, that is, we have input X and the bias. Yeah, input X and bias, and then we are going to compute let J. So when we zoom into this node, we see two elements, summation and the activation function, and then we can compute Yj. So Yj, that is F let, that means Yj F of this let, and then we can calculate Yj, that is this equation. And then once you know Yj, and then we feed it into all this output node. If we zoom into this output node, we will just find the same two elements. That is the summation as well as this function. Yeah, so y to YNH. So we have right here, including the bias. And then we can compute lat-k. Once we compute the lat-k, it depends on, and then we can write zk into this particular form. So yj, that is given right here. So if you are going to substitute yj into this point, and then so we are going to compute. We can represent we can relate the output z to x in this form. Yeah, so you can just find out that wk, that is right here. So what I did, that is just to substitute yj by this guy. So just this guy right here, and then include the wk0 right here. So that is the input-output equation for this neural network. Yeah. So when k, that is 1, and then we are talking about this output. It depends on all x right here, including the bias. And then so when we talk about k, that is 2, and then what you need to do is just to change the corresponding value of w, and then you can compute the value of z2, and also you can put it in this matrix form, and then this one, that is z1 z2 up to zc. Yeah, for this one, that is just one particular value of this z according to what value of that k it is. Yeah. So in the next slide, I'm going to show you how do we use this equation or construct this equation in a small example, so that we can use this single equation or we can use this matrix form. Yeah. Anyway, just to emphasize that, if we are going to use the backpropagation and then the algorithm to learn the connection weight w and wkj, we need the iteration to be differentiable. Yeah.